Hello, my name is Erin, and in this video I'm going to be talking about polymers. Polymers are ubiquitous in our everyday life and can be found in pretty much any industry and everywhere you go, from the plastic carrier bags we use in the supermarket to a police officer's bulletproof vest and even contraception. The reason why polymers have so many endless applications is because their molecular structures can vary so much, and molecular structure determines macroscopic properties. So, what is a polymer? A polymer is a molecule, so it is comprised of atoms which share their valence electrons in order to form covalent bonds. Some typical molecules that may come to mind include water, methane, and ammonia. These molecules are made up of a relatively small number of atoms, whereas polymers have molar masses that can range between the thousands and the millions, meaning that they must be made up of hundreds or even thousands of atoms, and are therefore known as macromolecules. Another feature of a polymer, apart from its incredible size, is that its structure repeats over and over again. This is because in order to form a polymer, you have to take a large number of monomers, which are smaller identical molecules, and bond them all together in order to form a long repeating chain. One very interesting application of polymers currently is their use as nanoscale drug delivery systems in the body. But before we look at this in more detail, it's important for us to consider the structure and the properties of the polymers that form these drug delivery systems. The polymers we will be considering are copolymers, which means they are made up of more than one different monomer. Here are some examples of how the monomers could be arranged relative to each other. We will be considering block copolymers, which is where there is separate blocks of each type of monomer within the polymer chain. Block copolymers are a type of chain growth polymer, also known as addition polymer, which simply means that when the monomers react together, no byproducts are generated, and that the mechanism by which the monomers bond together is by chain polymerization. To produce block copolymers, a specific type of chain polymerization must be carried out, known as anionic chain polymerization, but cationic and free radical chain polymerization also exist. Anionic polymerization begins with an initiation step. A nucleophile is used as an initiator, and it attacks one of the carbon atoms of the carbon-carbon double bond of the monomer. Carbon cannot break the octet rule, so as it forms a bond with the nucleophile, the pi bond of the carbon-carbon double bond must break heterolytically and the electrons move on to the other carbon atom. For this mechanism to work, the monomers must have a double bond, and the nucleophile we use must be very strong. For example, it must have a negative charge present on an atom with low electronegativity, so it can easily donate its electrons. We must also have an electron withdrawing group bonded to the carbon atom which receives the pi electrons in the mechanism. Here I have a benzene ring. The reason for this is because this reaction occurs between two electron-rich species, and this is very uncommon in organic chemistry. Here I have the resonance forms of the product from the mechanism. You can see with an electron withdrawing group, the negative charge can be delocalized across many atoms instead of staying on one. This increases the thermodynamic stability of the product and therefore makes the reaction between two electron-rich species feasible. Propagation occurs the same way as initiation. The negative charge that forms on the carbon atom in the initiation step reacts in the same way as the nucleophile did. Each reaction with another monomer reforms the negative charge on the carbon atom of the newly bonded monomer, so the process can repeat over and over again, progressively increasing the length of the polymer chain until all the monomers in the reaction mixture have been used up. After the mechanism is complete, the negative charge on the long polymer chain remains. This reactive end can either be terminated by the addition of an electrophile or can be protonated depending on what solvent is used. If neither of these is the case, the reactive end will remain and the polymer is said to be living. If a second monomer is added to the reaction mixture, anionic chain polymerization will occur, with the living polymer acting as the initiator. This will occur until all of the new monomer has reacted. This is how block copolymers are made, and this process can be repeated over and over again to get as many blocks as you like, and also the amount of monomer added can be varied to control the sizes of the block in the copolymer. One block can be hydrophobic, meaning it is nonpolar, and one block can be hydrophilic, meaning it contains polar bonds. that can interact or hydrogen bond with water molecules. In this case, the copolymer is known as an amphiphilic block copolymer, as it is both hydrophobic and hydrophilic at the same time. In an aqueous environment, the copolymer spontaneously forms micelles, which have hydrophobic cores protected by a hydrophilic shell. The Gibbs free energy for this assembly process is negative, and even though the ordering of the chains in this way decreases the entropy of the system, the entropy of the surroundings is increased much more by minimizing the contact of the hydrophobic block with the water molecules, so therefore the second law of thermodynamics is not violated. Many drugs which show high activity at curing cancer have been excluded by top pharmaceutical companies very early in their screening processes, as they've shown to be insoluble in water, and this makes them incompatible with our bodies. This is because, if taken orally, absorption into the body is low, and if injected, there is a high risk of aggregation of the molecules in our bloodstream. Nanocarriers offer a solution to this problem, as the drugs can be associated with the hydrophobic core of the micelle during the assembly process, and the hydrophilic shell allows the micelle to be easily transported around our bodies. Therefore, hydrophobic drugs can be transported at concentrations that exceed their maximum solubility in water. Drugs that have been used already include Taxol and doxorubicin, which work by causing cells to carry out apoptosis, also known as programmed self-death. One problem with conventional cancer treatments like chemotherapy is that all cells, including healthy ones, can be damaged. Nanocarriers also offer a way around this by using targeting techniques. For example, tumours have enhanced vascular permeability, which means that the gaps between the endothelial cells which make up the capillary wall are increased, allowing more passage across it. The small size of these micelles allows them to enter the tumour tissue from the bloodstream, but they are too large to pass from the bloodstream into regions where there are healthy cells. This is known as the EPR effect and leads to the drug containing micelles accumulating in the tumour tissue. This is also helped by the fact that cancer cells lack effective lymphatic drainage. This is an example of passive targeting, but active targeting is useful too, as some cancers like pancreatic cancer don't observe much of an increase in vascular permeability. Examples of active targeting include functionalizing the hydrophilic shell of the micelle by covalently bonding ligands to the hydrophilic block of the polymer. We can use antibodies which are specific to antigens found on the surface of the cancer cells, or we can use molecules which are specific to receptors that are overly expressed on the cancer cells. For example, some cancer cells have shown to overly express folate receptors, and therefore folic acid can be used as a receptor targeting ligand. Polyethylene glycol, or PEG for short, is a common polymer used as the hydrophilic block. It is biocompatible and has been shown to prevent the body having an immune response to the micelles. In one study, it was found that when a PEG shell was used, less than 30% of the micelles were uptaken in 5 hours, but without the PEG shell, 66% were uptaken within 5 minutes. Increased circulatory time makes the drugs more effective and means lower doses of the drugs can be used. Nanomedicine has many more applications than just treating cancer. It has the potential to treat diabetes and can be used in gene therapy. One of the applications that I find the most interesting is that micelles functionalized with naturally occurring peptides have the ability to cross the blood-brain barrier and transport zinc ions into the brain. Concentrations of zinc ions in the brain have been linked to depression, so this is a potential treatment of mental illness. If you would like any more reading on this topic, I put my references in the description. Thank you for watching.